All right, let's dive straight into exactly how DeepSeek V4 is achieving this insane state-of-the-art long context efficiency. Because as researchers, we're constantly pushing the boundaries of what these models can process, right? But let's be honest, we inevitably hit a massive architectural wall when we try to feed them millions of tokens. We all know the KV cache is literally our biggest bottleneck. So reducing its memory usage by 98%, which is a 128-fold reduction, completely changes the game. Think about the scale of that for a second. We're talking about running massive million-token context windows without, completely melting down our GPU clusters. It dramatically slashes both inference compute and hardware costs. So here's how we're going to break this whole architecture down together. We'll start at the root of the KV bottleneck, look at how they handle sequence compression, and then unpack the real magic, compressed sparse attention and heavily compressed attention, before tracking a raw token's actual journey through the network. Okay, setting the baseline here. Why do our traditional models just absolutely hit a brick wall when sequence lengths get into the millions? Well, standard multi-head attention, it's a total memory hog. It eats about 4 megabytes per token. Now, multi-query attention tried to fix this by sharing key and value vectors, which impressively dropped memory down to 31 kilobytes. But there's a huge catch. The performance degrades because the model just loses its ability to capture those complex, nuanced relationships between tokens. So DeepSeek realized we needed a complete paradigm shift. Instead of obsessing over compressing attention heads like grouped query attention does, they asked a fundamentally different question. What if we compress along the sequence dimension itself? Which brings us to the actual mechanics of sequence compression. How do they actually pull off merging tokens without destroying the underlying data? Let's say we want to compress 4 tokens into one. We can't just average them out, right? That would just dilute all the important signals with noise. Instead, we follow a really precise 4-step workflow to evaluate exactly how much each token should contribute, so we retain only the most vital signals. And this is where it gets really brilliant. It uses data-dependent weighting. Rather than just applying a blanket score, the model computes a distinct weight for every single dimension across those 512 dimensional vectors. It's essentially picking and choosing exactly which specific features are worth keeping, giving it an incredibly fine-grained control over the compression. But wait, if you just chop tokens into strict blocks of 4, you get these harsh artificial boundaries that totally disrupt context. So they use overlapping windows. This lets token information naturally bleed into adjacent overlapping groups, keeping a perfectly smooth, continuous flow of context throughout the sequence, rather than chopping it up. Okay, so now that our tokens are effectively compressed at the sequence level, let's look at the first of the 2 major attention mechanisms they deploy, compressed sparse attention, or CSA. CSA takes those sequence compressed tokens and pairs them up with what is basically a lightning-fast indexer. Even with tokens compressed 4-to-1, doing attention against all preceding entries is still way too slow. So this indexer acts as a ruthless filter, fetching only the absolutely vital data that actually matters for the full attention computation. It speeds up the throughput dramatically. Now, because heads are now sharing these higher dimensional KV vectors, computing the queries actually gets pretty computationally heavy. But they solve this beautifully with a low rank projection. Basically, they squeeze the math down through a smaller bottleneck and project it back up, which slashes the required parameters down to under 16%. So that's CSA. Now let's contrast that with its macro-level counterpart, heavily compressed attention, which is built specifically to handle those massive context windows. Unlike CSA's 4-to-1 ratio, HCA is wildly aggressive. We are talking about compressing 128 tokens into a single key value entry. This massive leap is exactly how the model achieves its crazy capacity for immense sequence processing. Because this compression is just so extreme, the KV cache footprint shrinks to the point where standard dense attention actually becomes computationally cheap again. We don't even need that sparse indexer here. The data footprint is so small that the model can afford to just look at everything all at once to quickly build broad global summaries. All right, let's put this all together. Let's map out a token's actual journey and see exactly how a raw embedding flows through this alternating dual system architecture from start to finish. This architecture is so intelligently scheduled. A raw token comes in, gets a broad global mix in the early layers,
enters an alternating refinement stage in the middle, and finally snaps into precise focus right before output. It essentially forces the network to refine representations at multiple levels of abstraction without incurring a quadratic compute penalty at every single layer.
I love this analogy. Think of HCA like a telescope. In those early layers, the model isn't obsessing over the exact grammar of a single sentence. It's looking through a telescope, getting a fast, wide-angle view of the overarching themes and global structures across a sequence of millions of tokens. But then, right after using the telescope, the model switches to CSC. It picks up a magnifying glass. Now it's scrutinizing those high-resolution, local token interactions. It's looking closely at immediate syntax and fine-grained logic, using that 4-to-1 sparse selection to maintain absolute precision. By rapidly swapping back and forth between the telescope and the magnifying glass in its middle layers, the model is constantly balancing this sweeping global context with really sharp, nuanced local details. It's extracting the absolute best of both worlds with incredible computational efficiency. Then, at the very end of the journey, the final layer abandons compression completely. It uses full attention to snap everything back into perfect focus. It maps that heavily refined data back out to a full, uncompressed token resolution, so we don't lose a single critical detail when generating the final output logits. So, seeing these massive memory savings with zero loss of detail, it really makes you wonder, right? How quickly is sequence-level compression going to become the mandatory standard for all future AI architectures? Because honestly, the efficiency gains here are just too staggering to ignore, and it fundamentally changes what's possible for the future of long-context computing.